Hey guys, so today we're starting our unit on annuities and mortgages. And you're probably, the first lesson is called the amount of annuity, and you're probably wondering what the heck is an annuity. So, an annuity is a savings plan where you make the same deposit at regular intervals. And it's usually for a long term. So, um, for example, you might have an RRSP, which is a registered retirement savings plan. So you're saving for your retirement, or an RESP, which is a registered educational savings plan that people will set up for their children, and save a little bit of money, like every month or every few months, over a long period of time. And it's kind of nice because if you let it sit for a long period of time and you just keep adding a little bit of money at a time, you end up with a lot. The interest tends to be higher, and you end up with a nice kind of retirement plan at the end that you can withdraw from, or a educational plan that you can pay for college with, or a university. The formula looks like this: A equals R 1 plus I to the n minus 1, these are ones, all divided by I. So there are a lot of letters in here, and I'm just going to explain what each letter means. So A is your amount of annuity, and it's the end amount. So it's kind of like, they also call it the FV, or the future value. So what is your annuity going to be worth in the future? That's mostly what we're solving for when we use this formula. R stands for regular deposit. So it is the amount of money that you are going to put in on a regular basis. And it's always the same amount. I is your annual interest rate. In decimal form divided by the number of compounding periods. Per year. And I'm going to show you how to do that in our example. And n is our total number of compounds. So it's usually like the number of compounding periods times the number of years that we have the annuity for. I'm going to show you an example. If you took the grade 11 and you did the compound interest, I and n, they're calculated the same way, but I'm going to remind you when we do our example. So let's move down the sheet and we'll do the example so you can see how it all works. So the one thing I like to do with the examples is highlight all the important stuff, and then I'll show you how I solve these problems. But first we're going to highlight. Anita deposited $800 in an account at the end of the year, at the end of every 6-month period for 7 years. The account paid 9% compounded semi-annually, so that's every 6 months. Determine the amount in the account at the end of 7 years. So what I like to do with this, when I start to solve it, is make a little list of A, R, I, and N. And I try to figure out what those are all first before I sub it into and I start to use the formula. Mostly because I have to calculate I and N first. So, Anita deposited $800 in account at the end of every 6 months. That's a regular deposit, so that's going to be R. So that's $800. N is over the amount of time, which is 7 years. And we're going to do it every 6 months, which is 2 times a year. So I'm going to times it by 2 to get 14. A is the amount at the end, and we don't know that. And the last one is I, which is our percentage in decimal form. So we have 9%, and I'm going to put that in decimal form, which is 0.09. And you're going to divide it by how many times a year you have it compounded. And it's compounded semi-annually, which is twice a year. So I'm going to divide by 2, which makes this 0.045. Now, once you have that, all you have to do is sub into the formula and solve. Now, big rule with this that I tell all my students is we're not going to round until we get to the very end. Round only at the end. All right. The reason we do that is to make sure our answer is as accurate as possible, especially when we're dealing with money. We don't want to be, if we round, we're going to be short on our end, or the bank will be short on their end, and we don't want that to happen. So we make sure we round only at the end and we carry as many digits as possible. So here's the formula. R 1 plus I to the exponent n minus 1 whole thing divided by I. So we'll sub it all in. 800 bracket 1 plus I, which is 0.045, to the exponent of 14 minus 1, the whole thing divided by 0.045. So you got to make sure that we are following BEDMAS when we do these. So I'm going to deal with everything in the brackets first, and then I'm going to multiply by 800, and then we're going to divide. So you kind of have to do all of the top first before you do the division. So 800, I'm going to show you guys as many steps as possible. 1.045, so I've added that to the 14 minus 1, all divided by 0.045. Then I'm going to do the exponent part. 1.045 to the exponent of 14, which is 1.851944922. See, I carried everything that I could. Minus 1. All divided by 0.045. We'll subtract the 1. So it becomes 0.851944922. Don't round, guys. And let's multiply and divide. So times 800, and then divide by 0.045. And I get 15,000. Oh, wrong thing. $15,145 and 60. Now we can round 69 cents. That's how you do that. So if I want to know, determine the amount in the account at the end of 7 years. Therefore, we have $15,145.69 in the account at the end of 7 years. let's move to the second page and I'll show you something else we can do with this. So sometimes it's really helpful if we know how much we should deposit on a regular basis in order to achieve a desired future amount. So let's say you're like, for my retirement, I want to have $1 million. Knowing how to find out what we should actually deposit every month is kind of a good thing to find out. So in this case, we're still going to use the annuity formula, but we're going to rearrange it. Now you guys should know how to rearrange it based on our last lesson, but let me give it to you. It looks like this. R equals A times I divided by 1 plus I to the n minus 1. So that is our formula to find out what our regular deposit is, and that can be really helpful. Let's see how that works with our this example. Andrew's 25. He plans to save. Let's highlight things. He plans to have 500,000 in a retirement fund when he retires in 40 years. Assume that on average, Andrew's deposits earn 6% compounded monthly for the next 40 years. What regular deposit must Andrew make to have the required amount of retirement? And how much does Andrew actually contribute to the account, and how much interest does he earn? So this is a very interesting type of question. Again, for the solution, I like to list everything. So I'm going to do another list and calculate my I and N for the things that I can. So A, in this case, is what do we want our future amount to be? They've told us this time, so we want it to be 500,000. R, that's what we're trying to find. How much do we have to deposit? I is our interest, 6% compounded monthly. So we'll turn the 6% into decimal form, 0.06, and we'll divide it by 12 because we're doing it monthly. And then N is 40 years. They've given that to us, but it's every month. So it's 480 times. Well, let's calculate that. Sorry, guys. 0.06 divided by 12, 0.005. Once you have all that, we're going to sub it into the formula just like we did before, except we're going to use this formula. 1 plus I to the n minus 1. So we got 500,000 times I, which is 0.005. 1 plus 0.005 to the 480 minus 1. Okay, again, when you do this, guys, remember to follow BEDMAS. So figure out what the bottom equals, figure out what the top equals, and then we'll divide it, all while we follow BEDMAS. So the top is really easy. 500,000 times 0.005, which is 2,500. I'm just going to move this up. All divided by 1.005 to the 480 minus 1. I'm going to calculate that whole thing. 1.005 to the exponent of 480 minus 1 which is 9.9574536 0.72. Again, do not round it, guys. And it will just divide. 9, 5, 7, 4, 5, 3, 6, 7, 2. And I get 251. And now we can round because we got to the end. 0.07. So therefore, if he wants to have 500,000 in 40 years, he's going to have to deposit $251.07 every month. That's not bad. It's kind of doable. B says, how much does Andrew actually contribute to the account? So B, if he makes a deposit of $251.07 and he does it 480 times. So let's calculate how much he actually deposits. 07 times 480 times 480 means he deposits $120,513.60. That's how much he actually puts into the account. And then for interest, it's just the difference between the 500,000 he would have at the end minus what he actually put in. So 500,000 minus the 120, 513.60 means he actually earned $379,486.40, which is actually not bad. That's a lot of interest. You actually make more interest than what you actually have to put in, and that's why these types of accounts are like extremely good for saving for retirement, because you're only putting in a portion and making the money work for you in terms of interest. So there you go. That's how you find an annuity. That's how you find the regular payment of an annuity. And that's how you figure out how much interest you actually make on an annuity. There's practice questions for you guys. I'll see you in the next lesson.